Now for question 1, to verify this function is indeed a solution to the ODE, we compute two sides of the equation. Okay, we compute two sides of the equation. The left-hand side, you just differentiate y with respect to x. So maybe the left-hand side equals the derivative of y with respect to x. The function is here. The function is y equals, if you want me to copy, so how about I just copy it here. We just differentiate the functions, so now let's say 2 times e to the power of x cubed over 3, right? We differentiate that. You have been taking calculus for a long time. You know how to differentiate that. You have to use chain rule, right? You have to use chain rule. Okay, you leave out the constant of 2. You probably okay. I will do the whole thing in 2 steps. You leave out the constant of 2, and then you differentiate e to the power of x cubed over 3. For this one, you have to use the chain rule. Okay, so to use the chain rule, you copy this 2 first. You choose the box as u, right? Again, to use the chain rule, choose u so that the given function as a function of u is simple to differentiate. You choose u to be the whole thing in the box, then the function as a function of u is e to the power of u. Differentiate e to the power of u, you have e to the power of u, right? You do not write u, I wrote u. You do not write u, so keep u in mind, okay? Do not write u, you write u in terms of x, in this particular case as x cubed over 3. Now you see why I spent a long time on chain rule, actually. That's x cubed. I'll try that again. You have x cubed over 3. And then, because u is a function of x, you have to keep on going. Differentiate the derivative of x cubed over 3 is equal to x squared, right? So you have the left-hand side, you have x squared then times e to the power of x. That's the left-hand side. So did I mess anything up? You have 2x squared then times e to the power of x cubed over 3. Okay, now let's compute the right-hand side. The right-hand side now is x squared times y. So because you are given y as a function of x, you just plug y into the function. So you have x squared and then times y is 2 times e to the power of x cubed over 3. Right. So do you see you have the same thing? The right-hand side is the same thing as 2 times x squared times e to the power of x cubed over 3. So you see the left-hand side is indeed the same as the right-hand side. Okay. In most cases, to verify something, you compute 2 sides of the equation, and then you verify the 2 sides are the same. That's how you verify the equation. Right? So we're done question 1. Okay. So any questions? Actually, the actual problem of solving an equation is something like, I give you an equation. You look at the mouse cursor. I give you an equation, a ODE. Okay, I give you an equation like that. Okay, you are looking for the functions. Now, for this one, it's actually the type we're talking about today. We'll have some ways to get the function. Anyway, you see at least from question 1, you see at least that function is a solution to the differential equation, right? ODE. Now look at question 2. In question 2, so we're trying to say for any constant a, it's actually a solution to the same equation. I'm trying to say the differential equation can have many solutions. In question 2, a can be any constant. A can be any constant. Do you know what I mean? In question 1, the solution is a particular case when a value is 2. Actually, a can be any number, any real number actually. Okay, now we'll work on question 2. In question 2, we verify that function is indeed a solution to the equation. The same idea. The solution to question 2. This time I think I can do it quicker. Compute two sides of the equation. The left hand side. I mean the left hand side. The left hand side. You compute the derivative of y with respect to x. By that we mean you differentiate the function a times e to the power of x cubed over 3. The same idea, you just replace 2 with a, so the same thing, right? You leave out a, you leave out the constant factor of a, okay, and then you differentiate e to the power of x cubed over 3. Using the chain rule, so we have seen that already. Using the chain rule to differentiate the function, you have a times x squared. X squared is the derivative of u. I meant u is x cubed over 3, and then times e to the power of x cubed over 3. Okay, that's the left hand side. Now the right hand side, I think it's kind of the same, right? The right hand side now is x squared times y. X squared times y. Sorry, so something in my throat. X squared times y. The same idea. You have x squared, and then you replace y with a times e to the power of x cubed over 3. You have the same thing, yeah, right? You have a times x squared times e to the power of x cubed over 3. So you see the left hand side is the same as the right hand side. We verified, okay. Again, the intention on question 2 is to show you, actually in almost all cases, so differential equation can have many solutions. In all the cases, okay, ODE has many solutions. So there's a constant involved in here. Okay, a can be 10, can be 2, can be 5, can be any real number, can be 0, can be any number. That's my intention on question 2. Simple, right? If you did not have any problem with question 1, question 2 is simple too. Now we work on question 3. In question 3, you have an equation, and actually you have two equations. The first one is ODE, right? Ordinary differential equation, right? The first one is a ODE. The second one is actually we call it a initial condition. Initial condition, okay. To make a convincing question, so can I replace 2 with some other number? Okay, I just use 2, okay, so just in case I mess anything up. The second equation is an initial condition. It means the value of the function y is equal to 2 when x value is 0. You listen to me carefully, okay? This equation, it means the value of the function y is equal to 0 when x value is. Now let me try again. I said something wrong. I'll start over, okay? This equation means the value of the function y is equal to 2 when x is 0. I said it right now. Okay. So the whole thing, a ODE, so together with a initial condition, the whole thing is called, you put the two things together, it's called an initial value problem. Now listen to me carefully, okay? In almost all the cases, a initial value problem has one and only one solution. By that we mean the initial condition can determine the constant. You look at question 2. Okay, in question 2 there's a constant, arbitrary constant a involved in the function, right? In the solution, I mean. Okay, and the initial condition in question 3 can be used to determine the constant. Okay, so that's why the initial value problem has a unique solution. We'll see how that works. Okay. Actually, you're going to see many questions like this. Okay. For question 3, we just understand the concept. So later on, you're going to see the idea over and over again. The initial condition is used to determine the constant. Okay. Now we just understand what is the meaning of initial value problem now. Okay. Now for question 3, so we have seen the function, the given function y equals 2 times x cubed over 3 is indeed a solution to the ODE, right? Is a solution to the differential equation of, let's say, y equals, I mean dy over dx equals x squared and then times y. So we have seen that in question 1 and question 2, right? Now all we need is to verify the initial condition is satisfied. Okay. Moreover, we want to compute the value for that function. We want to compute the value of the function when x is equal to 0. Okay. So maybe at x value of 0, y equals, you plug x value of 0 into the solution, into that solution. Okay, into that solution. So the value of y is 2 times e to the power of x value is 0. So exponent is nothing but 0, right? If you want, you can write that as 0 cubed over 3. The value of the function e to the power of 0 is equal to 1. So that's why the value of the function y when x value is 0 is equal to 2, right? So do you see the initial condition is satisfied? Initial condition is satisfied, right? So you write this whole line using one equation. It means the value of y when x value is 0 is equal to 2. So that is the solution to the initial value problem. So by that we mean it's a solution to the equation, and it's also the initial condition is satisfied as well, right? Okay, now let's look at question 4. You know everything. I guess so question 4 is my intention. I was trying to do in question 3. Okay. In question 4, we are trying to get the solution to the initial value problem of that. Again, one equation, one ODE, and one initial condition. You put these two things. You put the two things together. You have a initial value problem. Okay. My intention on question 4 is to show you the initial condition is used to determine the constant, and the solution to an initial value problem in most cases is one, only one. I mean, there's a unique solution to the initial value problem. I will show you the idea. Okay. So first of all, we have seen using question 2, okay, we have seen actually the solution in question 2 is called the general solution. For the people in Math 152, you know the meaning of the general solution. Any solution is in that form is called the general solution. Okay, we have seen the general solution to the ODE. Is using question 2, okay, as in the form that y equals a times e to the power of x cubed over 3. In that solution, a is an arbitrary constant. Okay, I will show you how to use the initial condition to determine the constant. Initial condition now is the value of the function. Okay, you look at the mouse cursor. The value of the function at 0 is equal to 3. Okay. Now because the value of the function y when x value is 0 is equal to 3, you just have to know the meaning of this notation. Okay, we have again the y value is 3. We have y value is 3 from that equation. Okay, from that equation, y value is 3, x value is 0 satisfies the equation. Okay, we have y value equals 3 is equal to a number a times e to the power of x value is 0. Okay, x value is 0, it means e to the power of 0 cubed over 3. Okay, so do you know the meaning? The circled is the general solution, and the initial condition says that the value of the function is equal to 3, y value is 3 when x value is 0, so the equation of that is satisfied. So do you see this equation actually shows you how to get the value of a? So it means the left hand side is 3, the right hand side is a times e to the power of 0, right? It means 3 is equal to a. It means the solution to the initial value problem. Okay, so can I write the final answer here? So the solution for question 4, okay, for question 4, the solution to the initial value problem is we have seen a value is 3. When a value is 3, the function becomes y equals 3 times e to the power of x cubed over 3, right? Again, the function we just got is the solution to the ODE of that with the initial condition of that. I'm trying to say the function we got is actually the solution to the initial value problem. You put two things together, you have an initial value problem. Okay. Any questions? Again, part 1 is designed to show you the meaning of the solution to a ODE and what we mean by the solution to a initial value problem. Okay. Now we move on to part 2. Part 2 is designed to show you how to find the solution for a special type. Actually, in the future, if you need the course, so differential equations, it's probably a second-year course. It's nothing too hard. So just for different types in the course, you're going to classify the types of ODEs and many other things. Okay, for different types, you have some techniques to solve that type. Okay, the first type, the simplest type. I mean, probably we are going to deal with it's called separable. Okay, by separable we mean the ODE can be rewritten in that form. On one side, you can put y on one side of the equation. It's also possible to put x on the other side. If that's the case, it's called separable. Okay. For separable, you'll use 3 steps. I think I summarized 5 steps. We used the 5 steps. Okay, A, B, C, D, and E. Okay. At this point, I do not read the 5 steps. We're going to use some particular questions to show you the meaning. Okay. Now we work on the questions to show you what is the meaning of separable ODEs. Okay. What is the meaning of all the steps? So don't worry, it's simple. We just cover one tab, separable. I think most institutions do not cover too many tabs. Actually, again, the differential equations should, in my view, is not part of the course. Okay, it's not part of the calculus 2. We're doing this for UBC. Okay, now question 1. Again, so do not lose track of the meaning. We are looking for a function. We are looking for a function satisfying the equation. In many cases, the function is hard to guess. I think many of you guys are smart. Can anybody guess the solution? Which function y as a function of x satisfying the equation? You do not know is the right answer now. Okay. Now I'm going to use that question to show you the meaning of the steps. Okay. I think it's not hard for me to switch screens. Okay. Now the solution. So first of all, it's possible to separate x and y on 2 sides of the equation. That's why we call this tab the separable. Okay. From the given equation, we separate x and y first. Okay. You know how you now you can treat the dy over dx as a quotient. It's permissible after we learn differentials, right? It's permissible to treat dy over dx, the derivative of y with respect to x, as a quotient. Okay, you treat dy over dx as a quotient now. Okay. From that equation, if you want me to recall, we can recall a property. I think in high school, junior high school, or elementary school, you call it the cross multiplication. I think that's the term. Okay. If you have an equation, so something like a over b equals c over d, then this equation is equivalent to the equation. So now let's say a times d, and then equals b times c, right? You cross multiply these two numbers is equal to cross multiplying b and c. Right? Of course, this equivalent is true only when b and d are not equal to 0. Cross multiply. Okay. If you do not want to use that property, you can just imagine you multiply 2 sides of the equation by dx, and then multiply 2 sides of the equation by y squared. You are going to have the following. Okay. So you put the y's together, so you have y squared dy, right, equals x squared dx. That's what I meant by separable. Okay. And by the way, not all equations are separable. Not all the ODEs are separable. We only deal with the separable ones. By that we mean it's possible to separate x and y on 2 sides of the equation. And not separable ones, I will show you some cases. Okay, So now let's say if you have an equation like dy over dx equals sine of x squared over y squared, right? It's not permissible to do that equation. So this way, this one is not separable. I mean, the underlying equation, the underlying ODE is not separable. Okay? So the technique cannot be used for that. Separate y and x. So the first step, okay. You look at in general, put the ODE. I'm going to remove the term linear. Okay, put the ODE in that form. I'm not introducing the term linear. Okay. It's possible to separate y and x. You put everything y on one side of the equation, and then you put everything x on the other side. It's possible, right? So we're done step 1. Okay. Step 2, we integrate two sides of the equation. We integrate two sides of the equation. Okay. After integrating, there should be a constant c involved. I will show you the meaning. Okay. It's kind of step 1. So did I label the number of steps in the general thing? It's step A. Okay. Can I use A instead? It's step A. We do that. Okay. I'm trying to label the items using the same notations as those in the step procedures. What do we do in step B? In step B, we integrate two sides of the equation. After integrating, there should be a constant, an arbitrary constant involved. Okay. I will tell you the meaning. Integrate the left hand side, you'll have the integral of y squared and dy, right? Integrate the right hand side, you have the integral of x squared and then dx. For the equation in question A, it's permissible. You just treat the left hand side as a differential of y. You treat the right hand side as the differential of x, a differential of x. Okay, and then you integrate two sides of the equation. C is not needed in here, so because implicitly in the notation there's a constant c involved, right? Now let's say, okay, I will show you the meaning. Now, to compute the left hand side, you get the integral, the indefinite integral of y squared in terms of y. Okay, in terms of y. And so be careful. There's a constant c involved in here. Okay, the antiderivative of y squared is 1/3 of y cubed, right? All of you guys know that. 1/3 of y cubed is the antiderivative of y squared. After getting rid of the integration notation, there should be a constant c involved. So temporarily, so can I just use c1? So because on the right hand side you have another constant c. Okay, and then integrate the right hand side. The same thing, you have 1/3 of x cubed, and then plus c2. Okay. Again, for an indefinite integral, for an indefinite integral, there should be a constant c involved. Okay. So do you see the whole thing can actually be written in terms of, I'm going to remove c1 from the left hand side, and for the right hand c2. For the right hand side, I can write the right hand side as in terms of c2 minus c1, right? Put that in brackets. You actually do not need c2 minus c1. C is a constant. It's arbitrary constant, okay. C1 is also a arbitrary constant. So that makes sense. C2 minus C1 is also a arbitrary constant. I think we have seen the same idea in Math 101 when we first did the calculus, when we first started the integrals, right? I'm trying to say for the right hand side, you just replace the whole thing with c. C is a constant, an arbitrary constant, I mean. Okay. So we have this. Right. That's a better thing about writing on computer. I can do that. I cannot do that on board, on blackboard or whiteboard. Okay. So we're done step B. I will show you the meaning of step B. Okay. In step B, you find the derivative, the integral of the function g of y and the two integrals. Okay. Actually, we are done step C already. So do you see we are done C already? Okay. Actually, in the general thing, I was trying to ask you to do the thing in 2 steps. For complicated cases, we do the thing in 2 steps. Okay. So we have the left hand side, so which is an antiderivative of g of y. Okay. On the right hand side, f of x, uppercase f of x is an antiderivative of lowercase f. Okay, and then plus c. In most cases, after you get this, so we're done the question. Okay, I'm sorry, I was not totally following the step procedures. So can I do it again? That's actually it's okay. I'm not going to redo it. It's not always possible. It's not always possible. I'm trying to say, if it's possible, I'm trying to say I'm done step B and step C. If you want to compare. I mean step C. It's not always possible, okay? But whenever possible, eventually you want to write y as a function of x. By that I mean try to solve the equation for y. Try to solve the equation for y, okay? Now I'm talking about whatever step. So can I just call it C? So the number of C may not be consistent with the step procedure. Probably is next year I'm going to rewrite the steps. But I'm trying to say originally we were trying to get y as a function of x, satisfying the ODE, right? So but here in general it may not be possible, but whenever possible, to try to do the following. Whenever possible, okay. Solve the equation for y, okay. So you multiply 2 sides of the equation by 3. I think you have y cubed is equal to x cubed, and then plus 3c, right? At this point, you could replace 3c with another c or a or whatever notation you want, okay? But if you want to solve the equation for y, okay, y is equal to cube root of x cubed and then plus 3c. If you want, you could write y as in terms of cube root of x cubed and then plus a instead. And then you can say something like where a is an arbitrary constant. For this part, I do not really care. You could just write 3c as long as you know 3c is a constant, arbitrary constant. It doesn't matter. Okay. So we're done the solution. If you really want, you could verify this function. The function we got is indeed the solution to the ODE. Okay. But I think all of you guys have no trouble to differentiate the function. I'm not doing it. Okay. Any questions about this? We're done question 1. It's actually simple, so it's not hard at all. Okay. To summarize a little bit, separate y and x. You treat the two sides of the equation in that. You look at the mouse cursor as differentials. Okay, the left hand side is a differential of y, the right hand side is a differential of x, and then you integrate two sides of the equation. Okay, so do not forget the constant after getting the answer to the indefinite integrals. So there should be a constant c involved. Okay, and then whenever possible, solve the equation for y. Write y as a function of x. So that's everything. Okay. I was trying to make some comments. I forgot. I was trying to make some more comments. It's okay. I could see the comments from other questions. Now we move on to question 2. Okay. The same ODE, right? So just with a initial value problem. For question 1, the equation, the ODE, has many solutions. So because A, it can be any number, right? A can be any number. Yeah, you can take cube root of any number. You could also take cube root of negative numbers in particular, right? I was trying to say A, it can be any number. Now we'll do question 2. The same equation, just with a initial condition. So the whole thing, you put the two things together, a ODE and the initial condition, we call the two things initial value problem. Okay. Maybe from question 1, so we see we have the general solution, right? The general solution. To the ODE. The general solution is y equals, I think, cube root of x cubed plus a. I think I got it right. Y equals cube root of x cubed plus a. A is a constant. Now all we need is to determine the constant. Okay. All we need is to use the initial condition to determine the constant. Okay. Now because the value of the function y when x value is 0 is equal to 2, you plug this thing into the general solution. In most cases, you can determine the constant there. Okay, so we'll see what's going on. Okay, the value of y is 2. You just compare the general solution when y value is 2, x value is 0. Okay, again, so do not be confused about the meaning of this notation. The meaning of the notation is y value is 2 when x value is 0. Y value is 2, okay, and x value is 0. 2 is equal to cube root of x value is 0, right? 0 cubed is 0, and then plus a. You see you have a equation of a. Solve the equation for a, and you can get the constant, right? And by the way, a little bit more comment. It's also possible to determine the constant. You look at the mouse cursor from here, after you get the solution. Before, I'm trying to say it's possible to determine the constant. So before solving the equation for y, I want to repeat, it's possible to determine the constant before solving the equation for y. You could do it from here or from here. Okay. But since we got the general solution already, we get the value of a from here. Okay. Scared me. So are you still there? I saw a message saying bad connection or something. Can somebody confirm you can?
Yes, sir.
Okay, sure, thank you. Cool. Okay, from here we're going to solve the equation for A. I cannot afford to lose any more classes. My time is pretty tight. So this semester we lost too many classes already. Too many holidays. Also, we still have what's that day? So Good Friday, right? Easter Monday. We're going to lose another day. Solve the equation for A. You take the cube of two sides of the equation. I think I can keep on going from here. 2 cubed, 2 cubed. I think you have 8, right? And then, so by that we mean you take the cube of two sides of the equation. And then the right hand side you have 0. I do not write 0. I do not have to write 0. The right hand side is cube root of A, and then the whole thing cubed. It's nothing but A. Okay. It's easy to get the number, but the important thing is the initial condition is used to determine the constant. In the general solution, you have a constant A, right? And then you use the initial condition. You can determine the value of the constant. A value is 8. Okay. So maybe now therefore in question 2 we are trying to get the solution to the initial value problem. Okay. The solution, I will write the full sentence now. Okay. The solution to the given initial value problem. Problem is you replace A with 8, right? So you have y equals cube root of, x cubed and then plus 8. You could verify all the conditions are satisfied. So by that I mean you could verify the function is indeed the solution to the ODE, and also the function satisfies initial condition. I'm trying to say the two things are satisfied. Okay. So we're done question 2. Again, my intention on question 2 is trying to show you again the initial condition can be used to determine the constant. In almost all the cases, the solution to a initial value problem is unique. Okay, now we move on to question 3. Okay. So probably question 3 was the question I used to motivate the definition of a solution to ODEs. If you have y prime in all the cases, for your purpose of course, for separable ODEs, in all the cases, write the prime notation using dy dx notation, using the Leibniz notation, okay, using the d notation. The question is equivalent, the same thing as the following, okay, dy over dx, the derivative of y, right, equals x squared over y. Okay. Why we do that? It's because we want to separate y and x. This notation is essentially the same thing. Now we treat dy as the differential of y. We treat dx as the differential of x. Okay. Again, it's permissible to treat dy over dx as a fraction now, as a quotient now. So you can multiply two sides of the equation by something. Right? I will include so this thing as part of the solution, just so that you can remember. If you see the prime notation, convert the prime notation to dy dx notation. Okay. Now it's possible to separate y and x, right? So the equation now is equivalent to dy. You look at the mouse cursor. It's permissible to bring down that y as the denominator on the left hand side. It's essentially dy over y and equals x squared and then times dx. It's possible to do that. Whenever it's possible to separate y and x, you have a separable ODE. Okay. This one is separable, right? For this one, I guess we can integrate two sides of the equation. Actually, in many cases, if after separating x and y, if either side is very hard to evaluate, I'm trying to say if either side you have to use the techniques like the substitution or whatever other things, integration by parts or something. Try to do two sides of the thing separately. Okay. I will show you the meaning using some other questions. Okay. But anyhow, in this case, it's possible to separate. We have a separable ODE, right? The next thing we do is to integrate two sides of the equation. Equation is true. The integral of two sides of the equation is also true, right? I mean, if you take the integrals of two sides of the equation, they equal 2. They're equal to, I mean, okay. Okay, now the integral of the left hand side is the same thing as the integral of the right hand side. Okay. And the left hand side is easy, right? The integral of 1 over y, I believe is natural log of absolute value of y. So do not forget the absolute value. It's kind of important now. Okay. It's equal to the right hand side. We have seen it many times. It's equal to x cubed over 3. So can I just write that as x cubed over 3 and then plus c, right? So do not forget c after integrating two sides of the equation. So do not forget c. Okay. We could finish here, but in general, it's easier to see. I'm trying to say it's also possible to write the solution in a better form. I'm trying to say if you have a question like that on the final, if you stop here, I could give you the 4 points. I'm going to give you all the points. So the rest of the thing I'm doing now is to write the solution to some way better form. Still, it's important, okay? Still, you have to listen to me now. It's super important now. What I'm doing next is to write the solution to way better form. In particular, I'm going to solve the equation for y. Whenever possible, you probably want to do that. Okay? Solve the equation for y now. Okay. So do you remember? Probably I can do this on the next slide. So do you remember if you have so now let's say natural log of a equals b. Okay. If I want you to solve the equation for a, how do you write the a in terms of b? This equation is always the same thing as a is equal to e to the power of b. So do you want to recall how to compute natural log of a? So now let's say natural log of e. Yeah. To compute that, you think the base e to what power is equal to e, right? You think the base e to what power is equal to that e. I'm trying to say these two equations are equivalent, are the same. Okay. I do not want to make too many comments. It's actually from the definition of logs. Any log is the same thing. Natural log is a log with the base of e, right? I'm trying to say you you go back to here. I'm trying to say from the equation it's possible to write the absolute value of y in terms of x as e to the power of x cubed over 3. You're not done yet, okay? X cubed over 3. And then plus c. Can I use brackets here? I just want to indicate the whole thing in the brackets as e to the power of that thing. Okay. Exponent, I mean. Okay. The whole thing in the brackets are that. So do not ask me why I'm doing the following. I'm just trying to rewrite the solution to a better form, actually to a way better form. Okay. We keep on going. Okay. The absolute value of y is equal to still I do not want to run too fast. Now I want you to recall a property like this. For any base a to the power of, so now let's say m plus n is equal to a to the power of m and then times a to the power of n. I'm going to use that property next. Okay. The base now is e. You learned that in high school, actually probably in junior high school. Okay. The next thing we do is to rewrite the solution to the form that e to the power of x cubed over 3, okay, and then times e to the power of c. Okay. Absolute value of y is equal to that. It's comparable to the following. I'm trying to review too many junior high school or high school math. Okay. If I give you the absolute value of y is equal to 2, now how do you write y? How do you solve that equation for y? Y is equal to plus or minus 2. You learned that, right? Okay. Again, so don't be confused. After you get this, the underlined, then you have the complete solution to question 3. I'm just trying to rewrite the solution to a way better form. Solve the equation for y and write y in way better form. Okay, so this time y is equal to the absolute value of y is equal to that. So y is equal to e to the power of c. I mean plus or minus e to the power of c and then times e to the power of x cubed over 3. Okay. Now c is a constant, arbitrary constant, okay? And then e to the power of c is an arbitrary positive number. So let's do me carefully, okay? I want to repeat. C is an arbitrary constant, so e to the power of c is an arbitrary positive number. E to the power of c is always positive, right? And then plus or minus c is an arbitrary non-zero number. Plus or minus, I mean the whole thing in that circle, the whole thing in the circle is an arbitrary positive number. I'm going to replace that number with a, okay? So the solution to the given ODE in question 3 is in the form that a times e to the power of x cubed over 3, okay? According to the solution, a is an arbitrary positive number. Now let me try again. I said something wrong, okay? According to the argument, a is an arbitrary non-zero number. A is an arbitrary non-zero number, okay? One little more comment, okay? But when a value is 0, you can check the constant function y equals 0 is also a solution to the ODE. So we can treat a as an arbitrary number. Now, actually, I spent a long time to make this point. So maybe where a is a arbitrary, arbitrary. A as an arbitrary constant. Again, so don't worry too much about the thing I did in here. As I was just trying to write the solution y as a function of x in a super nice form. Okay. In most cases, after you get the underlined, then you are done. Okay, you can get all the points. Any questions on question 3? So do you see it's actually the question I used to motivate the concept of the solution to ODEs? If you look at part 1, so this is the function I used in part 1, right? That's the equation I used in part 1. Okay, differential equation in here. I was trying to tell you why this one is a solution to that ODE. Okay. So we're done question 3. We move on to question 4. Okay. Actually, we did a very similar question to 4 already. It's a initial value problem. An ODE with initial condition. It's a initial value problem. I'll try to make it bigger. I know the screen on your end is smaller. I will make it bigger. Okay. Now the solution. So from question 3. From question 3, we have seen the function y equals, I mean the general solution to the ODE. The general solution to the ODE is y equals a to the power of e, a times e to the power of x cubed over 3, is that right? We have been using the same function many times. Okay, I think that's what we got. Now let's recall the initial value can be, initial condition. Initial condition can be used to determine the constant. Initial value problem. Okay. Now since that condition, it means the value of the function y is equal to 1. The value of the function y is equal to 1 when x is equal to 0. Okay. We have you look at the circle, y is equal to 0. Y is equal to 1 when x is 0. Okay. So y is equal to 1 when x is 0. We have 1 equals a times e to the power of 0 cubed over 3. So we have a value is 1. Okay. So because e to the power of 0 is equal to 1. So the solution to question 4 is unique. Okay. The general solution, there's a constant a involved, but for the initial value problem, the solution is unique. I'm trying to say maybe therefore what? Therefore, the solution to the initial value problem. Okay. The initial value problem. The initial value problem has the solution. One and only one solution. Okay. Has the solution. I was trying to make a little space for the solution. Has the solution y equals a value is 1. The solution is nothing but e to the power of x cubed over 3. Right. Okay, now it's 227, right? We keep on going. Separable. The equation is separable, right? Separate y and x first, right? So you have dy over y squared plus 1 equals dx. You put everything y on the left hand side, you put everything x on the other side. Okay. And then we integrate two sides of the equation. So we have the integral of the left hand side is that equals the right hand side. You just have the integral of dx. The integrand is 1. Okay. Now we get the antiderivatives of two sides of the equations. So antiderivative of 1 over y squared plus 1, I think we have inverse tan. Is that right? We have inverse tan. We have inverse tan of y for the left hand side. Okay. For the right hand side, you have antiderivative of x. I mean antiderivative of 1, you just have x and then plus c. Okay. In most cases, if you get that, then you have done this, the general solution. I mean the general solution. Okay. For this one, I want to recall something again. Okay. Separable. It means it's possible to separate y and x. You put everything. It's possible to put everything y on one side of the equation. You put everything involving x on the other side. That's why we have a separable ODE. Okay. And then what you do after separating, and then it's possible to integrate two sides of the equation, right? After that, so do not forget C. Okay. For this one, it's probably still easier to determine the constant C after we solve the equation for y. In most cases, solve the equation for y first. Okay. Or it's also possible to determine the C from here. We'll keep on going to solve the equation for y first. Okay. If inverse tan of y is equal to x plus c, you know y is equal to tan of x plus c. Recall the definition of inverse tan. Okay. At this point, we have the general solution to the equation, right? So this is the general solution to the equation. In the general solution, you have C. The general solution has a C. Okay, it means the equation without initial condition, it has many solutions. Every value of C is a particular solution. Now the given question is a initial value problem. It means the value of the function y when x value is equal to 1, the y value is 0. Okay. And then we use the condition. We use the condition to determine C. Okay. We have the value of y is equal to 0 when x value is 1. Okay. Is equal to tan of 1 plus c. Am I lost? Again, it means the y value is 0 when x value is 1. Okay. So we have tan of an angle. Now you treat the whole thing in brackets as an angle. Okay. When the value of tan is equal to 0. When the value of tan is equal to 0, 1 plus c has to be 0. Okay. Actually, it's because in the solution you have an inverse tan involved. Okay. We just I will keep on writing. So, okay. So, we're trying to think tan of what angle in radian is equal to 0. For a reason, so we have 1 plus c is equal to 0, right? It probably is easier to determine the value of c from here, from the general solution in that form. But I'm cheating a little bit. Okay, I will see if I can have a better solution. But I'm trying to say you take inverse tan on two sides of the equation. You have 1 plus c is equal to 0. So you have c value equals -1. Okay. So what? c value is -1, and then the solution to the initial value problem is given by y equals tan of c value is 1, tan of x minus 1. That's the solution to the initial value problem. So give me one little moment. Actually, if you determine the constant c from here, 1 plus c can also be the numbers like pi. Tan of pi is also 0. Yeah, tan of pi is also 0. I'm trying to think why c cannot be pi. Okay. So anybody want to tell me why c cannot be pi? Yeah, that's why I said it's probably easier to determine the constant c from here. Okay. Again, I could be cheated a little bit in here, but it's not in my mind. It's not in my mind right now. Okay. I will try to see if I can figure it out, but I want to move on. Yeah. In any case, you have at least one particular solution to the question, right? I want to move on now. Okay. So write down question 5. I could be cheated a tiny little bit. Actually, question number 6. I want to include question number 6 as one of assignment questions. I want to move on to 7. But yeah, because I remember there's a little tricky thing in question 7. Question number 6 is nothing tricky. Okay. Okay, now for question number 7. The two variables in 7 are u and t, so the same thing, right? You just treat u as y, you just treat t as x. Now the solution to the question. Okay. Separate u and t first. So by that we mean on left hand side, I believe you have 2u and then times du. Then is equal to, on the right hand side you have 2t and then plus secant of t the whole thing squared. And then dt, right? dt. It's called a separable equation. I mean ODE, ordinary, so differential equation. It's because it's possible to separate u and t. Okay. So do I get everything right? And then what we do is to integrate two sides of the equation. Okay, we integrate two sides of the equation. We have the integral of 2u and then du is equal to, on the right hand side you have the integral of 2t and then plus secant of t the whole thing squared dt. Okay, now we compute the two integrals on two sides of the equation. You have antiderivative of 2u. I think you have u squared. Right, you have u squared. Antiderivative of 2u is u squared. You think which function has the derivative of 2u, right? You have u squared. And then on the right hand side you have t squared. And then plus antiderivative of secant squared of t, so which is tan of t, right? That's in the basic formula. All of you guys know that, okay? And then plus a arbitrary constant c. Okay. Now we have the general solution. Okay. And then to determine the constant c, we use the initial condition. The initial condition gives you the value of u is equal to 0. I mean the value of u is equal to -5 when c I mean when t value is 0, right? Can I start a new page? That's the line we got on the last slide, right? I'm going to copy initial condition. So because the value of u is equal to -5 when t is 0. We have, so can we try to determine the constant from here? So we have the value of u is -5. You have -5 the whole thing squared is equal to, and then the t value is 0. 0 squared is equal to 0, right? 0 squared, and then plus tan of 0, and then plus c, right? So do you see the initial condition will give you the value of c? C is actually 25, right? C is 25. So because c value is 25, so you have u squared is equal to t squared and then plus tan of t, and then plus 25. At this point, you could say you have the solution to the problem. Okay. But if in most cases I want you to solve the equation for u, I want to write in this particular case u as a function of t. Okay. If we write u as a function of t, so we have u equals, so do not be confused. If u squared is something like, if u squared is 4, then u has to be plus or minus 2. Okay. So u is equal to plus or minus square root of t squared, and then plus tan of t, and then plus 25. I remember there's a little tricky thing in here. So do you want to tell me, so do you take the positive sign or minus sign for the solution? Do you take the positive sign or negative sign for the solution? I want you to look at initial condition again, please. The circled. I want you to look at the circled again. In many cases, I'm trying to say you have to use the condition over and over again to figure out something. In this particular case, my question was u is equal to plus or minus the whole radical. My question is, do we take the positive sign or negative sign? We take the negative sign. Yeah, we take the negative sign only. Okay. So because if you take the positive sign, so there's no way for u value to be -5. So do you know what I mean? In this question, we have used the initial condition twice. Now because, okay, initial condition again, u of 0 is equal to -5. We have, I don't know what I'm writing. We have the positive sign is gone. U is, you just take the negative sign. Okay, negative square root of t squared and then plus tan of t. So there are too many t's. So can I use brackets here? Or otherwise the notation is tant, right? Tan of t and then plus 25. I'm trying to say, using initial condition again, you have to keep the negative sign only. Any questions? Again, if you have that as the general solution, then I can give you all the points. But negative sign is kind of essential in here. So do you see the meaning? The value of u is -5 when t value is 0. You have to keep the negative sign only. I have decided to go back to question number 6. Okay, so because it's kind of, you could be confused if okay, I will go back to question number 6. Actually, I was trying to cover everything today, but it doesn't matter now. Whenever you see the prime notation, in order to separate y and x, write the y prime notation in terms of dy over dx, treating dy over dx as a quotient. Okay. Now the solution to question number 6. The first thing you do is x times cos of x, and then equals, right, 2y, and then plus e to the power of 3y. Okay. And then in any case, rewrite y prime in terms of dy over dx, so that you can see it's possible to separate y and x, so the equation is separable. Okay. After that, it's possible to separate x and y, so the equation now is equivalent. It doesn't matter you put x on either side. I'm trying to say, on the left hand side, I want to include x, everything x. Okay, everything x is going to be x times cos of x and then dx. Now the right hand side is 2y plus e to the power of 3y in brackets dy. I still kind of see the brackets are essential. Okay, although many people do not use that. Now to integrate the left hand side in particular, you need to use the, what rule do we use? We need to use the integration by parts. Right? It's a typical form for using integration by parts. Represented by that question, my intention is to show you if on either side the integral is a little bit more tedious to evaluate, a little bit long to evaluate, you need to use the other techniques. Try to evaluate the integral on two sides separately. Okay. You still can write the next step. You want to evaluate the integral of the two sides of the equation are equal. Okay. You also have x times cos of x and then dx equals the integral of the right hand side, 2y in brackets e, and then plus e to the power of 3y and then dy. Okay. At this point, I want probably it's easier if it's less messy. It's less messy if you integrate the two sides of the equation separately. Okay. So maybe at this point, for maybe try something like where the left hand side is so maybe, sorry. I need a new slide. At this point, we evaluate two sides separately. Okay. For the left hand side, x cos of x, the integral of that. You know we have to use integration by parts, right? We let you choose u and dv. This one is a simple function simple integral for which you need to use the integration by parts. You let u be x and the dv be cos of x dx, right? And then you compute du is dx, and v, for v you get a particular antiderivative of cos of x, so which is sine of x, right? Using integration by parts, you have the left hand side. The left hand side is x cos of x. It's in the form of u dv, which is the same thing as u times v. I'm talking about the by parts formula. Okay, by parts formula uv is x sine of x minus v du. V du is the integral of sine of x dx. So the whole left hand side, I mean, okay, is equal to x times sine of x, and then antiderivative of cos of x is negative. I mean, antiderivative of sine of x is negative cos of x, so you plus cos of x. Yeah, in any case, whenever you evaluate an indefinite integral, you have to plus a c, but we're going to use c later for other things. So can you write c1 in here? I think the integral of the right hand side is simple. Okay, now I just copy the left hand side. I mean x times sine of x, and then plus cos of x equals, we integrate the right hand side. Antiderivative of 2y, you have y squared, right? And then plus antiderivative of e to the power of 3y. I believe you can remember we have been seeing this over and over again. So do not forget the 1/3. Okay, you have 1/3 times e to the power of 3y. I want to use c in here. Okay, plus c. All right. For this one, it's not quite possible. I'm trying to say it's not quite possible to solve the equation for y. You can just leave the general solution. I'm trying to say you can just leave the general solution in that form. Okay. Lastly, we have to determine the constant, right? To determine the constant, it means the value of y is equal to 0 when x value is 0. Okay. Now, so because you do not have to write it now, of course, the value of y is equal to 0 when x value is 0. So we have we're trying to use that to determine the value of c. On the left hand side, we have 0 times sine of 0 and then plus cos of 0, right, equals y value is 0 too, right? So we have 0 squared and then plus 1/3 of e to the power of 3 times 0 and then plus c. Okay. I think on the left hand side, you sine of 0 is 0. You just have cos of 0. Okay, cos of 0 is equal to 1. The left hand side, this one is coming from cos of 0, right? So what's the right hand side? I think the right hand side you have something like 1/3 of, you just have 1/3, right? You look at the mouse cursor, 1/3, and then e to the power of 0 is equal to 1. You do not have to write the factor of 1. And then plus c. This will determine the constant, okay? The value of c in that solution is equal to 1 minus 1/3. I think you have 2 over 3, is that right? You have 2 over 3. Now, the particular solution to the initial value problem, I think I copied everything in. I think I can just write it here. The solution to the initial value problem. I forgot C already. 2 over 3. You replace C with 2 over 3. Okay. For this one, again, it's not very possible to solve for y. I'm trying to say it's not quite possible to write y in terms of x. You can stop here. We now work on question 2. Okay. In question 2, the population of bacteria is x of t. We use x of t to denote the population. Okay. At any time t, it grows continuously at a rate of 70% per hour. We also have the condition that the initial population has the size of 100. When the time t is 0, the population size is 100. Okay. And then it grows at a rate of 70% per hour. In question A, we are trying to find the population size in terms of time t. By that we mean we are trying to get the population size at any time t. Okay, now the solution. To do question A, we are going to set up an equation. We are going to see the rate of change in 2 ways. Okay. The bacteria grows continuously at a rate of 70% per hour. It means the rate of change is 70% on the current population. I will write something down. Okay. The instantaneous rate of change. Instantaneous, so rate of change of the population is 70% on the current population, so which is 0.7, and then times the current population. We are going to use x of t. I just write x. Okay. On the other hand, the instantaneous rate of change is the derivative of function x with respect to t. Recall what we learned in Math 101 in Calculus 1 when we did related rates. So the instantaneous rate of change can be represented by two things. I mean, the same rate of change is represented by two things. So we have we'll copy this to the next slide. So we'll continue from here. This equation is separable. By that we mean it's possible to separate x and y on two sides of the equation. Now we have, on the left hand side, we have dx over x. We move x to the denominator here. We are going to leave the constant 0.7 on the right hand side. So we have dx over x is 0.7 and then times dt. So you see it's possible to separate x and y on two sides of the equation. The equation is separable, right? To solve the equation for x, for the function, we integrate two sides of the equation. So we have the integral of the left hand side, dx over x, is equal to the integral of the right hand side, so it is 0.7, and then times dt, right? The integral of the left hand side is natural log of the absolute value of x, and then the integral of the right hand side is 0.7t. Okay. At this point, do not forget to plus c. Okay. Now we are going to solve the equation for x. We are going to write x in terms of t. We are going to write x as a function of t in a nice form. So we have the absolute value of x. The absolute value of x is equal to e to the power of 0.7t and then plus c. Which means the absolute value of x is equal to, using the property, something like e to the power of, now let's say m plus n equals e to the power of m and then times e to the power of n. So the absolute value of x is equal to e to the power of c and then times e to the power of 0.7t. So x equals, again we want to write x as a function of t in some nicer form. So x is equal to plus or minus e to the power of c and then times e to the power of 0.7t. Okay. Again, we are trying to find the general solution to the equation, the circled equation, okay, at this point. Now, you listen to me carefully. C is a arbitrary constant, so e to the power of c is a arbitrary positive number, and the plus or minus c is represents any non-negative number. But x, the constant function x value of 0, is also a solution to the equation. It's simple to check. Okay. So I can replace the circled part, everything in that box, with a arbitrary number a. So x is equal to a constant a, arbitrary constant a. Now a can be any number, positive or negative, 0, a arbitrary number a, times e to the power of 0.7t. Okay. That is the general solution to the equation. Now let's go back to the question. Actually, implicitly there's an initial condition involved there. Okay. In the question, we have the initial population has the size of 100. It means when at time t value of 0, the population size is 100. Okay. Now, by the condition, in the question, we have the population size is equal to 100 at time t value of 0. It means x of 0 is equal to 100, right? When time is 0, there are 100 bacteria. Use that condition, we can determine the value of a. Now let's recall the initial condition can determine the value of the constant. Okay. So we have the value of x equals 100. You look at that equation. You look at the underlined. X value is 100 when t value is 0. So we have 100 equals a, the constant, and then times e to the power of 0.7 times the t value of 0. Okay. You look at the mouse cursor now, okay? E to the power of 0 is equal to 1. So the equation shows the constant value of A is equal to 100 using initial condition. Now we are ready to have the answer to question A. So maybe thus x of t, x of t, x equals, A value is 100, so we have 100 times e to the power of 0.7 and then times t. Okay, I can write that as x of t to mean x is a function of t. The population size is changing in terms of time t. So that's the answer to question A. So questions B, C, and D are designed to better understand the meaning of the function. We'll keep on working. Okay. The answer to question A is x of t. The population size is equal to 100 times e to the power of 0.7t. Okay. Using that, we are going to the question B. You look at the question B. We are looking for the population size after 3 hours. It means we are trying to compute the population size when t value is equal to 3. Okay. So we compute the population size of x when t value is 3. We plug 3 into the function. So the number is computed using 100 and then times e to the power of 0.7. Now t value is equal to 3 times 3. Is 16. It's 17. So the answer is 817. We round up. We round the number up to a whole number. Okay. Now let's look at question C. In question C, we'll try to determine when will the population size reach 500. To do that, we are going to solve an equation for t. We are looking for time. When will the population size reach 500? Okay. Now we solve the following equation. For t, the equation is we want the population size to be 500. We are looking for t. The population size at any time is given by, according to question A, is given by 100 times e to the power of 0.7t, right? We divide two sides of the equation by 100. So we have e to the power of 0.7t equals 5 after dividing two sides of the equation by 100. And this equation is equivalent to 0.7t equals natural log of 5. Review log you learned from high school if you do not remember. Okay. So the time needed is equal to natural log of 5 over 0.7. Using a calculator, natural log of 5 over 0.7 is 2.29. If we round the number to 1 decimal place, it's 2.3. So we have this number is approximated by 2.3. So the population size after 3 hours, I mean for question C, after 2.3 hours, the population size will reach 500. There's only one question remaining. We'll work on question D now. Okay. We still need the answer to A. In question A, the function, the population size in terms of time t is given by 100 times e to the power of 0.7t. Okay. Now we'll work on question D. In question D, we're trying to determine the time, the length of the time needed to take for the population to triple. Okay. We'll introduce a notation and then we solve an equation for the length of time needed for the population to triple. Maybe we let uppercase T be the time needed for the population to triple. Actually, the following argument is true for at any time. I mean, at any time for the population, starting from any time, the time needed for the population to triple is always the same. And then, now let's get an equation of t, okay, an equation of uppercase t. Now let's think at any time lowercase t, the population size is given by 100 and then times e to the power of 0.7t. So this is the population at time t. Okay, and then starting from time t, after the length of time uppercase t, the population size is given by 100 and then times e to the power of 0.7 and then times t plus t. I'm going to write the meaning of this one. So this is the population at the time t plus uppercase t. Okay. And then after uppercase t, the population size will triple. What is the relation between these two numbers? The relation between these two numbers, so because the population will triple after starting from time lowercase t, after the time uppercase t, the population size is going to triple, right? So we have the right hand side is actually 3 times the left hand side. So that makes sense? So all we need now is to solve that equation for uppercase t, for the big T. We'll do that on the next slide. Now for the left hand side, I'm going to write the left hand side as 300 times e to the power of 0.7t. For the right hand side, I'm going to write the right hand side as 100 times e to the power of 0.7t, and then plus 0.7 uppercase t. The left hand side now is 300 times e to the power of 0.7t. The right hand side now is 100 times e to the power of 0.7t, and then times e to the power of 0.7 uppercase t. Now you have a common fact. I think on two sides, I'm trying to say on two sides you have a common factor of 100 times e to the power of 0.7t. You divide two sides of the equation by 100 times e to the power of 0.7t. I mean, you divide the equation by the whole thing in the brackets. You have 3 equals e to the power of 0.7 uppercase t. Now we are ready to solve this equation for uppercase t. This equation is actually the same thing as 0.7t equals natural log of 3, if you can recall the definition of natural log. I mean 0.7 uppercase t is equal to natural log of 3. Okay. So uppercase t now is equal to natural log of 3 over 0.7, which is approximated by natural log of 3 over 0.7. Enter everything on your calculator. This number is approximately 1.6 if you want to round the number to one decimal place. 1.6. I will write the answer to the last question. It means the population size will triple every 1.6 hours. Therefore, the population size triples every 1.6 hours. That's the answer to question D. We are now ready to look at exponential growth and decays in general. Suppose that there's a quantity changing continuously according to time t at a rate of k per unit time. When k is positive, we have a growth. When k is negative, we have a decay. In the question we just did, the quantity is the population of bacteria. The growth rate is 70% per hour, or 0.7 in decimal. For the general case, if at the beginning of the time the quantity has the value of x0, using exactly the same argument, we have x of t equals x0, the value of the quantity at the beginning of the time, times e to the power of kt. Because there's an exponential function involved, we call it exponential growth or decay. Again, when k is positive, we have a exponential growth, and when k is negative, we have a exponential decay.